Good evening, everyone. My name is Jyoti Sharma. Can you please confirm whether I'm audible or not?
Yes, ma'am, you're audible.
Thank you, Chitali. Okay, so this session is from 7 to 9, and let's start with the week 2. This is the brief that what we will cover today. So today we will cover like some introduction about the pollution, and then among that pollution we have two major pollution. That first is the water pollution, and another one is the air pollution. So we will talk about the some concept and the numerical related to water pollution as well as related to the air pollution. So this is what we will cover today, and this is basically the summary lecture of the from lecture number 6 to 10. Okay. So firstly, I will start with some general question on pollution, and then we will move to the air pollution and the water pollution. So I start with very basic question, and that first question is, dash is the introduction of contaminants slash harmful material into the natural environment that cause adverse change. And we have four options here: pollutant, pollution, runoff, and sewage. You can write in the chat box the answer whatever you are thinking it is right, and even if like you have some doubt in a b c or d, you can also write so that I must know that you have confusion or you have the clear idea about the answer so that I can explain accordingly. So Venkateshwara Rao gave me answer a, that is pollutant, but I'm expecting more answers. Okay, so I'm getting A answer, that is the pollutant, but no, I think you people are getting confused in option A and B, because there is a like the one is the phenomena or the situation, and another one is the substance or some material. So I'm not asking about the material, but I'm talking about the phenomena or the situation where some contaminant or some harmful material can be added into the environment. So that kind of situation or that kind of phenomena is known as what? Okay, Venkateshwara changed the option from A to B, but okay. Okay, so right now I'm getting B answer, and yes, I will also stick with the answer B, that is the pollution. So let me show you the difference. I think you were getting little confused, but just see here. Pollution is like you can say it is a phenomena or it is a situation when we do introduce this harmful substance into the environment, in the natural environment. So this will be the pollution. But pollutant is some substance or material, and that would be harmful for the environment, and whenever we are putting that into the environment, that substance is the pollutant, but that phenomena or that situation is the pollution. So I think right now the difference between what is pollution and what is pollutant is clear now. Okay, so we are moving to the next question. If you have any doubt still, you can write in the chat box. I will try to answer your question. Okay, so the next is little confusing, but I think you can solve this. Dash is the subset of the dash in the context of its impact. And right now we have four option: contaminant, pollutant, contaminant, pollution, contaminant, pollutant, contamination. Little trickier, but I think you can solve this. Try to solve. Otherwise, I will obviously I will tell you the right answer and with the explanation. See with the question mark. Priscilla. Okay, try next. Okay, someone gave me Vishal gave me D answer. Mm, no. Okay, so right now what we are talking about is the substance and like in the context of its impact. So just assume that something is like this, and then the part of, okay, let me use the pen. Okay, something is like this, and the part of this is something like this. So the thing is, we have two substances. The one is pollutant, and the another is contaminant. Okay, so what's the difference? And because here we are talking about in the context of the impact, so the outer part is the contaminant, and this is the pollutant. So why this is? Because contaminant is the introduction of something new substance in the environment. So this is contaminant, and if we are talking about its impact, then it may be harmful or it may not be harmful for us. For example, if we are introducing CO2 but in the lesser amount, or let's say if we are introducing some new gas but it may or may not be harmful for us, right? So whenever we are putting something foreign substance into the environment, that will be the contaminant. So that substance will be contaminant, and that phenomena will be the contamination. But it is not necessary that it will be harmful. Okay, so this may be harmful and may not be harmful. Okay, but the subset of this is the pollutant, because it is always harmful in the nature. So that's why the answer B will be right. Yes. So just keep in mind. But if we are talking like right now we are talking in the context of the impact only, but if we are changing the context, this may also change. I will show you in the next slide. But just keep in the mind that the introduction of the foreign substance, that substance maybe is known as the contaminant, and that contaminant may be harmful or not. If it is a harmful to the environment, then it is the pollutant, right? So that's how pollutant is the subset of the contaminant in the context of its impact. So that's how the B answer will be right. If you have any problem, you can let me know. Otherwise, we are moving to the next slide. Okay, just see here. I just wanted to give you little explanation. Contaminants are the foreign substance, right? But it is not necessary that it would be harmful for us. So in that case, pollutant is the subset of the contaminant. But if we are seeing that if we are seeing either it is a foreign substance or not, pollutant may not be foreign substance. So you have to see the difference, right? Okay, so next question is related to the point source and area source of the pollution. And this question is, which of the following is an example of a point source of pollution? And we have four options here. Rainwater runoff from agricultural fields, a diesel truck emitting black smoke from its tailpipe, floodwater carrying garbage into a lake, and leaching of pesticide from multiple farms. Pradeep gave me B answer. Venkateshwara also gave me B answer. And Priscilla also gave me B answer. Kuntia, if I'm pronouncing it right. Okay, so everyone is giving me the B answer. Yes, I will stick with B answer only. So there are two things. The first is the point source of pollution, and the second is area source of pollution or non-point source of solution. Sorry, not solution, but the pollution. So let me show you this graph. Okay, so if you are seeing here that there is a pipe, and if like we have a so if we do have very recognizable source of pollution, then this will be the point source, and very well defined source of the pollution, then this will be the point source. So for example, if we are having any pipe from industry or from household, from kitchen, and if that pipe is giving the wastewater and emitting this wastewater into the river, then this will be the point source. But here, if you will see, let me change the color. Here, if you are seeing that this is the cropland, and a lot of area is giving the pollution to the river, so we do not know from where exactly this pollution is coming from. So this will be the non point source of the pollution. Okay, so these are the differences between these two. Okay, here we also have some explanation that point sources are identifiable points or places that we can easily locate. And this is the example that I already have given you in the MCQ. And non-point sources are the one where it is difficult to identify the exact origin of the pollution. So this is how we can differentiate between whether this is point or non-point. So can you tell me, like, if we want to treat something, if we want to reduce the pollution, then which source of the pollution will be more difficult for us to reduce, either it is a point source or non point source? If we want to treat, let's say, the wastewater, uh, it would be easier for us to treat that point source or non point source. Can you tell me?
Concept. It will be easier for concept.
Yes, so it will be easier for us to treat the point source rather than non-point source, because like we do not have a very defined area from where it is coming, and like the whole area is spreaded from where this, for example, we have the agricultural land and we are having fertilizer in our farmland, and that fertilizer with the water that will go to the river. Okay, but it may not necessary that it will go through a pipe. Okay, so this is how it will be very difficult for us to contain that fertilizer based wastewater treatment, right? So this is how this is difficult for us. Okay, here again you can also see, whenever we are talking about the municipal wastewater, then industrial wastewater or tributaries, that would come under the point sources. But in the non-point sources, this will be untreated sewage, agricultural runoff, urban and suburban runoff, and the groundwater. Uh, okay, so it would be easier to treat the point source rather than non-point source. Okay, this one is, I think, very easier because I already have given you explanation. So which scenario best represents a non-point source of pollution? Wastewater discharge through a factory pipe into a stream, oil spill from a docked ship, sewage leaking from a non-pipeline, and rainwater carrying fertilizer and animal waste into river from farmlands. Venkateshwara gave me the answer. Any more answer that I can expect? Okay, so we already have discussed. Yes, Chitali also gave me the answer. So yes, the answer is the right one because it is the rainwater, and we do not have a well-defined pipeline or the area from where it will this waste or this pollution will go to the tributary. Let's say, so this is how D answer is the right one. Okay, so we have four phenomena, or you can say the processes: dispersion, dilution, deposition, and degradation, and what kind of impact it will have on the pollutant in the environment. So I have four options: increase their toxicity, make them more visible, reduce their concentration and change them into new pollutant. So, for example, if we have chimney and out of the chimney we have some smoke, okay, and then there is dispersion, dilution, deposition, and degradation of that smoke. Then what will happen? What do you think? What will happen to that? Priscilla gave me C answer. Chetali also gave me.
If C reduce their concentration.
Yes, so the answer will be that would reduce the concentration. So, let me show you something. Okay, so for example, if we have pollutants, right, this pollutant can be primary pollutant or can be secondary pollutant. I will discuss about this, but just keep in mind we have the pollutant, and if that pollutant will be emitted, so this will be the emission in the environment. So whenever there will be emission in the environment, it will be there will be dispersion. So dispersion is in the influence of wind, it will go from one place to another, and this is how this will dilute the condition, this will reduce the concentration at that one point. So it means when there was higher concentration just above the chimney, but when the wind will come, this will be dispersed. So per volume, there will be less concentration of the pollutant. Then there would be dilution, then degradation. So, for example, uh, there is a something. Let's say we have NO2, or let's say NO, that may have some reaction with another chemical, and this is how this can be changed into something else. So and it can be break down into something else, so this is the degradation. So that concentration is that concentration is getting decreased. Then there may be deposition. So for example, if we have rainfall and we have a lot of particulate matter in our environment, whenever there will be the rain, that particulate matter or dust, you can say, will be deposited on the rod, or let's say on the surface. So this is how this will clarify the environment. So the deposition will also help us to reduce the concentration, and that's why the dispersion, dilution, degradation, deposition, this will reduce the pollutant. So these, we can say, these are the natural processes by which we can reduce the pollutant in the environment, right? And I also have definition of this. Let me show you. So dispersion is the smoke disperses in the environment, and this is how this will no longer noticeable away from the source. If we are talking about the dilution, then again, I think you know the definition of dilution. Then deposition, so this will settle down, and degradation means breakdown of some pollutant into some non-harmful substance. So this will be come under the degradation. So I think now you are clear about this four terminology right here. Coming to the next question. So these are the basics of the pollution only. Then we will move to the air pollution and water pollution. But before that, I just wanted to make you clear about the terminology related to the pollution. Anyway, so which type of pollutant remain in the environment without breaking down naturally? So soluble pollutant, diluted pollutant, persistent pollutant, and deposited pollutant. What do you think? What is the right answer? Vijay Chandran's gave me C answer. Pradeep Chetali also gave me C answer. Yes. So I also agree with the answer C. That is the persistent pollutant. Persistent means nothing but like that can remain longer into the environment, that will come under the persistent pollutant. So we have a lot of man-made chemicals that has been released into the environment, and it take a lot of time to degrade that. So it is something like we can't degrade that naturally, we need ultraviolet radiation. So for example, if we do have CFCs, chlorofluorocarbon, we can't degrade, or the natural processes cannot degrade CFCs in the troposphere. Okay, so what will happen, these CFCs can only be break down by the ultraviolet radiation. So first, that CFCs, chlorofluorocarbon, have to move from troposphere to stratosphere. And in the stratosphere we have the ultraviolet radiation. That ultraviolet radiation can break down these CFCs into chlorine atoms, or let's say fluorine atom, and this is how we can break down this. But it is not like we can't break down in the troposphere. So this is how this will become under the persistent pollutant. And if okay, so POPs are persistent organic pollutant. Okay, so this is persistent organic pollutant, and we have two category of this. The one is intentionally produced, and another one is unintentionally produced. Intentionally produced, we will have industrial chemicals and organochlorine pesticides. And if we have unintentionally, means there are side product, or side product that we can have after getting intentional product. So this may be PAH. Can you tell me the full form of PAH? Polycyclic aromatic hydrocarbons, dioxins and furans. And these are something very dangerous. This can even these are carcinogenic in nature that can cause the cancer. And if you know, if we have something, some fuel if we have, and if we are like giving the heat, but in the absence of oxygen at the high temperature, then this will be known as the incineration, right? So in the absence of oxygen, if we are doing the combustion, then this will be the, and this will give you something, a hydrogen derived compound, and plus this can give you the dioxin and furans. So these are very harmful, and these are mostly released after incineration. Anyway, okay, so right now we know the terminology of the pollution. We know the difference between pollution, pollutant, contamination, contaminants, uh, then point source, a non-point source. We know about this, right? Then right now we are moving to the wastewater related questions. Okay, so if you want to assess the water quality, and if you want to assess the physical parameter, then what would be physical parameter among your four options? And we the options are BOD, then turbidity, nitrate, and total organic carbon. You can write in the chat box whatever answer you are thinking is right. I will try to correct you. Okay, Priscilla gave me B answer, and Venkateshwara also gave me B answer. Okay, and can you tell me? Okay, so yes, I also agree with this, that uh, yes. So answer is B, that is the turbidity. But can you tell me more physical parameter based on which we can assess the water quality? So the one is turbidity. What more physical parameter we have, based on that we can assess the water quality? Color, yes. What else? Taste, yes. What else? Hardness, not hardness, because hardness will come under chemical. Then temperature, yes. pH, you can say yes. What else? Anyway, so I will show you. But if we are talking about the physical parameter, then one is the turbidity, and let me show you what you mean by turbidity. So this is something, the turbidity. We have the clean water. Then if we are not able, like if 100% of the light is not getting transmitted, then it means we have some turbidity. The water is turbid in nature, and we can measure it in the unit, that is the NTU. So here you can say, here we have 10 NTU, then 25, 50, 100, and 250. And based on that, we can also assess the water quality, because we know that whenever the NTU is low, then uh, like indirectly we can say that the quality may be good. Okay, but along with that, we also need to measure some other thing, because if we have H2SO4, H2SO4 turbidity is very low. This is something like this, but we can't say that this is the water. So based on that, we have to also measure the chemical property of water, so that we can differentiate. So along with the physical, we need chemical, we need biochemical. But if we are talking about the physical parameters, then one is the turbidity, then one may be the total suspended particle, how much suspended particle we have, let's say in the water. Turbidity we already have like talked about. Then we have total dissolved solute. So we have suspended and the dissolve. Then conductivity is also the part of the physical parameter. Then color, temperature, taste, and odor. So this will come under the physical property of the water. Okay, so and you also must know the unit of it. If we are talking about the total dissolved solute, then this will be mg per liter. Then turbidity unit is NTU. Total dissolved solute is mg per liter. Conductivity, this is microsimon per centimeter. Then if we are talking about the color, then this is the Hazen units. Temperature we can measure in degree Celsius, Fahrenheit, Kelvin. Then if we have taste and odor, that is the qualitative in nature, that is not quantitative. Okay, the next is again very simple, but we will talk about this. Which of these is not a chemical contaminant? Sulfate, manganese, viral particles, and fluoride. Venkateshwara, Pradeep, they gave me C answer. Vishal also gave me C answer. Okay, so C answer is the right, obviously, because this viral particle will come under biological contaminants, but not under chemical contaminants. Okay, so right now, if we are talking about the chemical contaminants, so can you categorize? Like physical parameter, you also gave me the list of the physical parameter. Based on that, we can assess the water quality. But if I'm asking you to give me the list of the chemical contaminants that we may have in the water, then what that can be? Can you write in the chat box? Chemical contaminants in the water. If we want to measure whether like our water quality is good or not based on the chemical contamination, then what that factor or parameter can be? The one that Pradeep gave me in the last question, that was the hardness. because this is calcium and magnesium presence. So this is something chemical contaminants. Microorganism will come under biological contaminants, but will not come under chemical contaminants. Then what else we can put into that? Some cations. Can you give me the example of some cations? It's okay. We are just discussing the things. We have cations, we have anions, some metals, inorganic chemicals. Yes, we can have. So whenever we have cations, anions, obviously, so magnesium, iron, cadmium, so this will come under, for example, cadmium will come under metal, then magnesium will come under hardness, then we have, let's say we have sodium, then this will come under cation. If we have chloride, then this will come under anions. So a lot of chemicals we have that will be the part of chemical contaminants, right? Yes. So let me show you the list. So for the anions, we have sulfate, chloride, nitrate, phosphate. For the cation, we have potassium, iron, and manganese. For the hardness, we have calcium, magnesium. For salinity, I will tell you this sodium absorption. And then heavy metals, we have mercury, lead, cadmium, chromium. These are very harmful. Then other we may have arsenic, fluoride. So we will talk about this, but these will come under the chemical contaminant of the water. So let me just show you. And the thing is, it is very important for us to know the sources of each of this contaminant in the wastewater. So for example, if it is a sulfate, then from where the sulfates will come, either it will come from the industrial waste or from mining or from detergent. Other sources maybe, but the most prominent sources are mining and the detergent. And what kind of impact it will have on the environment or even on the health, then this we need to know. If it is the chloride, then fluoride is the major problem, as we already have discussed in the previous week, that chloride will lead to the skeletal issue, or it will decay the tooth. If we have the low concentration, then this is the beneficial for teeth. For example, if you have seen the toothpaste, then there must be written here the concentration of fluoride it have, and if it is in excess, then it may lead to the molting of the teeth. Then we have the phosphate, again it is from detergent and fertilizer. Then we have nitrate, nitrite. Then if we are talking about the cations, then this will, again we have potassium, iron, manganese. Then hardness, this is mostly caused by the calcium and magnesium. Salinity, if we have salinity problem in the water, then this we can measure using sodium absorption ratio and residual sodium carbonate. Then we have metal. These are very important because these metal we use in each of the electrical appliances. And whenever we have this pollutant in the wastewater or the water, then this will have a very harmful impact on the human body. Then we have others, but anyway. Okay, next we are coming to the another category, and that category is, you will tell me the category, but the question is, what category does BOD, that is the biochemical oxygen demand, fall under in water quality assessment? So we have four options: microbiological, physical, chemical, biochemical instability. What do you think? What should be the answer for this? Pradeep gave me microbiological, but I think we have to change the answer. Okay, Tanushree also gave me A. Pradeep gave me D. Yes. Okay, so I'm getting a uh, mix answer, that is DAC. But I want to just tell you that this is something will come under the biochemical instability. Then D answer is the right. Okay, let me tell you. Physical, we already have discussed, right? Turbidity, then dissolved, suspended, dissolved solute, then color, taste. This will come under the physical. So this can't be the answer, right? Chemical, we already have discussed. It is cation, it is anion, it is metal, it is uh, hardness. So the chemical is also not the answer. If we are talking about the microbial, then we must have some microbe. For example, if we must have a virus, bacteria, then this will come under the microbiological. But here we are talking about the mix of the biology and the chemical. So this is something, so biochemical oxygen demand, I already have discussed about it. But what is that? If we have microbes and we have organic compounds, that microorganism will degrade or will break down this organic compound into very simpler substances, for example CO2 and water. But for that, we have to spend some oxygen. So how much oxygen we need? Okay, so how much oxygen we need to degrade this organic compound into inorganic compound in the presence of microbes? Okay, so this is something we are talking about the microbes, but we are talking about the oxygen demand also. So this will come under the biochemical instability. So that's how D answer will be the right one. And among that, we have BOD, that is the biochemical oxygen demand. How much oxygen we need to degrade that organic compound into inorganic compound by microbes. So that will be the BOD. The COD is like we can use some oxidant or oxidizing agent. That oxidizing agent can degrade that organic compound into inorganic compound, simpler substances. So this will come under the chemical organic demand. So this is the COD. Then we have total organic carbon and the natural organic carbon. So here we are talking about the organic compounds, we are talking about the microorganisms. So this is how this is the biochemical instability. So I just want to summarize how we can measure the wastewater pollutant. So by the physical parameter we already have discussed, by chemical parameters, by biochemical instability parameters, and we can also measure it by microbiological parameter. So if we are checking this, based on that we can categorize that what kind of wastewater it is, what kind of pollutant we have in that wastewater, and then it would be easier for us to treat that, because we do know the property of that wastewater right now. Either it is physical property or chemical property or biochemical instability or microbes that we have in the wastewater. So based on that we can treat it now easily, because we do know the property of the wastewater. Okay, so now we are moving because we have some contaminants or pollutant in the aquifer as well. So but before that I should know that whether you know what aquifer is. So the question is, which of the following best defines an aquifer? So I have four options. A confined space within the earth crust where tectonic pressure stores fresh water. The second is a permeable groundwater layer or formation of rock or unconsolidated material that transmits and stores groundwater. C is a surface water body naturally replenished by underground spring and precipitation. And D is a subsurface zone where water is stored in impermeable bedrock layer with no percolation. Then this is just the definition of the aquifer. The one gave me D answer and one gave me B answer. Okay, so I will go with the B answer. Uh, and why the B answer? Because here in the D it is written that with no percolation. But if you know, yes, Chetali also gave me B right answer. Then no percolation means okay. So the groundwater is the part of aquifer. Okay, and groundwater is not stagnant in nature. It is moving. Okay, so there is a percolation also. So if I'm talking that there is a no percolation, then we are not talking about the aquifer. This is something else. Okay, so let me show you the figure. So B answer is the right one. Just see here. So these are the confining bed. So from this we can't move the water. So these are very impermeable layers. So these are the impermeable layers. But in between that, we have permeable layer. So this is permeable layer. This is impermeable layers. And this is also saturated layer. So all the spores of the soil or all the spores of that space has been filled with the water. So this part this part is permeable and also is saturated with the water. And that's how, if you have seen like in mountain area or in some area that some wall or some springs that we have, and that spring is giving you the continuously water. So this will come under from the confined aquifers. But if we are talking about the groundwater, then groundwater will come from this unconfined aquifer, because we do not have impermeable bed above that. So that's why this is unconfined aquifer. And this will give you the water table. So this is water table, and we have to dig to get water from it. So we can have some wall from where we can get the water, and we can also have some like whatever we are using, different technology by which we can extract the water. So just keep in mind, we have two type of aquifer. The one is confined aquifer and another is unconfined aquifer. And confined aquifer is if we do have two impermeable layers below and above to that. But just keep in mind, we have permeable layer in between that. So this is the permeable, so the water will flow. Okay, water will flow from one place to the another. Water is not stagnant in the groundwater, right? So that's how. Let me show you the answer again. So this is the permeable underground layer or the formation of rock or unconsolidated material that transmit and store groundwater. So that's how B is the right answer. Okay, as I told you that groundwater flows, right? And if we have some contamination in the groundwater, then what will happen? It will also flow, right? And we have one terminology, that is advective flow. So what that refers to? Now we have four options: the random molecular movement of contaminants in still water, the movement of contaminants due to chemical adsorption on soil particle, transport of contaminants carried by the bulk movement of groundwater influenced by the hydraulic gradient and aquifer properties. And the another one is the upward movement of groundwater through capillary action in dry soils. Okay, let me see the answers. Priscilla gave me C, and Amruta also gave me C answer. Can I expect more answer? What do you mean by advective flow? So adductive, so for example, this is your groundwater, right? And in that groundwater, we may have some contaminant. So for example, this is the contaminant that we have. So that contaminant will also flow, but how this will be flow? This will be flow based on the advective flow, and this is nothing but because this groundwater is also moving. Okay, so with that, this will also move, right? Yes, so that's how this will move with the groundwater, the first thing. And how this will move, so how the another question is how groundwater moves as well. So this is something like this. If we do have this groundwater, and let me change the color of this. So if you are seeing that this is the height h1 and this is the height h2, then there is a hydraulic gradient and this is the distance L. So hydraulic gradient is h1 minus h2 upon L. So this is your hydraulic gradient. So uh, whenever you will have higher hydraulic gradient, then the movement of the groundwater will be higher. And if we do have movement of groundwater, then contaminant will also move. The another is, as Chetali also gave me, that through pores and cracks in soil and rocks. Yes. So we also have the aquifer property. Aquifer have different permeability. So for example, if we have more clay in the aquifer, or if we have more silt in the aquifer, more granite we have in aquifer, so based on that, the permeability will also dependent on that aquifer property. So how much pore we have in the soil, or so such kind of things will decide the movement of the contaminants in the groundwater. So that's how C answer is the right one. Okay, Chitali told me advection and the capillary action. There is a difference between capillary action and advection. So advection is something even you have heard in the wind. So whenever you have, for example, if you have water, and this water will move in the atmosphere from with the wind. Okay, so this will come under advection. So this will come under advection flow. Okay, because the air is moving, either air is moving or water is moving, and with that energy is transferring, so that will come under the advection. But capillary is something, like we have the connection, one molecule connection with the another one, and then we have the pore space, and that if we have some gradient. Okay, so gradient, this gradient is not the hydraulic gradient, but this is the concentration gradient. For example, in the top soil we do not have higher water, but in the lower soil we have the higher water. Then there is a gradient, and that spores, the water will reach from lower level to higher level because of that gradient. So that will come under the capillaries. And I told you, in the aquifer we do have the saturated situation. Saturated means all the spores already has been filled with the water. So here the capillary action will not come under aquifer, aquifer based situation. And if we are talking about the groundwater, then we are talking about the aquifer, and capillary will not come under uh, groundwater contamination based advective flow. I think this is clear, because here we are talking about the saturated flow, not unsaturated. In the unsaturated we have the concentration gradient, but here in the groundwater we have the saturated, all spores already have been filled with the water. Then the capillary action will not work here. So this is how C answer is the right one. Okay, so there is a one formula and the one law, that is the Darcy law. And which of the following best represent Darcy law for the liquid flow through a porous medium? Because aquifer is the porous medium, and if we want to, so for example, this is our aquifer. So this is our aquifer, and if we want to flow the groundwater into that, so groundwater is the liquid. So the movement of this ground liquid flow will dependent on what? So based on that we have the Darcy law. So you have to, and this Q is the flow rate. So this flow rate will dependent on what kind of parameters? So this is something will come under the Darcy law. So can you tell me the right answer? A is the area. uh, dH upon dl is the hydraulic gradient, as I already have discussed. P is the pressure. uh, Rho is the density. G, the gravity. Okay, let me see the answer that you have given to me. Okay, so I have C answer. Priscilla and Pradeep gave me C answer. Yes. So I will also go with the C answer. So this Q is the flow rate. Okay. This K is the permeability coefficient. Then this is the area, as I told you. Like we may have granite, we may have silt, if we may have aquifer may have made up of clay. So based on that, permeability will be different. So this is the permeability coefficient. This is area, how much area we have. And this is something hydraulic gradient, as I already have told you. Whenever this is H2, this is H1, and this is L. So H2 minus H1 upon L. So this will be the hydraulic gradient. So based on that, the groundwater will flow in a particular direction. So this is not like that groundwater can move in any of the direction, but this will follow the Darcy law, and that Darcy law says that this is dependent on permeability, then area, and the hydraulic gradient. uh, then let me show you. Okay, so okay, so this is something I already have told you. This is H1, H2, this is length, and this is your aquifer. Based on that, this will be dependent on, right? Okay, Pradeep have asked me the one question. Why is the minus sign? Why is the minus sign for? So can anybody tell why this minus sign is here in this equation? Any guess?
It is
Mm-hmm.
in actual condition it is H2 minus H1. But if we are
This is
representing actually if we are representing it, it will be in H1 minus H2. Sorry, actually on representation it is H1 minus H2.
mm-hmm.
In order to get it in positive value, we are adopting that minus sign.
Okay. So yes, because here hydraulic gradient is the answer is exactly right, because the hydraulic gradient here is typically negative, because whenever we are considering from higher to lower head, so that's how this will give you the negative sign. Okay. Okay, so coming to the next question. Okay, because here in that equation, let me show you again. So this was the equation, right? K, then this hydraulic gradient and area. So this is the permeability coefficient, and just let me show you the values of this permeability coefficient. So or you can say that hydraulic conductivity also. and the value you can see for the clay value and for the loam. So just I just want to tell you that different area may have different aquifer material, and based on that the permeability coefficient, or you can say the hydraulic conductivity, may be different. Okay. Okay, this question is just based on the Darcy law, and I want you to solve this. And this question is something like that: a confined aquifer that have the thickness of 25 meter has two monitoring wall. So this wall and this wall spaced 600 meter. So the space is 600 meter along with the direction of the groundwater flow. So the ground water is flowing. Uh, 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 Groundwater is flowing. Okay. The difference in water level in the wall is 3 meter. So this is something it is telling that the difference between H1 and H2 is 3 meter. Then the hydraulic conductivity is 50 meter per day. So this is something K, hydraulic conductivity. And you need to estimate the rate of flow per meter of distance perpendicular to the flow. So I think you can calculate it using only the same Darcy law, that is Q is equal to K, then I A. This I is nothing but that dH upon dL. Okay, so let me show you the how we can solve this. So answer will be C. So this is how we can solve. So first we will calculate the gradient. We have 3 upon 600 meter. This is how this will give you the gradient. Then we have this formula we already have discussed, that K, A, and then the gradient. K is given 50, and this will come under area. Okay, because the thickness is giving and then the 1 meter, so this will give you the area, and this we already have calculated from here. So this is how this will give you the flow rate. So I think that would be easier for you to solve such kind of question on the Darcy law. Okay, so okay, but we have some limitation of the Darcy law, and this question is based on that limitation only. So while Darcy law is widely used to estimate groundwater flow, it is limited in predicting contaminant transport because it does not account for. And we have four options: hydraulic gradient and saturated flow condition, aquifer permeability and porosity, dispersion, diffusion, adsorption process affecting contaminants, and water viscosity and aquifer depth. Priscilla gave me C with the question mark. Okay. Amrutha gave me C answer. Yes. Yes, I also agree with the C. Yes. So because Darcy law only talked about the gradient, that is the hydraulic gradient, talked about aquifer property, and talked about the area. But it may be that contaminant itself can disperse, itself can diffuse, itself can adsorb. So if it is getting adsorbed on the surface, then how it will move? It will not move, right? So this is how there is a one term known as the retardation factor as well. So there may be such condition. So for example, using that, so in the Darcy law we had this KIA, and from that we can also estimate the velocity, right? So this is known as the Darcy velocity. If you know that meter square meter cube per second is something, the unit that we have of the flow rate, and this is meter square. And what we can do is, if we are changing between these two things, then what we can get, we can get the velocity as well. So velocity will be something like ki. Okay, because if that a will divided by q will be divided by a, that will give you the velocity meter per second. So this is known as the Darcy velocity. But this Darcy velocity is only like if we are talking about the dispersion, diffusion and absorption, then in real situation this Darcy velocity may be different from the real velocity of the contaminant. Okay, that velocity may be higher or may be lower as comparison to the Darcy velocity, and that is because that we are not talking about the property of that contaminant itself. The property may be, it may be adsorbed, it may be that it can be clogged into the pore space, then how this will move, or let's say it is getting diluted, or it is getting diffused. So there is a difference between dispersion and diffusion. Also you must know the difference between these two. But anyway, so the thing is Darcy velocity can be different from the real velocity of the contaminant, and that is because Darcy velocity did not account dispersion, diffusion and the adsorption process that may affect the contaminants, right? Okay, that is the same question. Anyway, so because I was talking about that the velocity can be higher or lower, it means that the contaminant transport can be resisted. Okay, the flow can be resisted of that contaminant, and there is the one terminology known as the retardation factor. So if we have the retardation factor 5, then what that means too. So we have four options. The contaminant moves 5 times faster than the groundwater due to increased solubility. B is 80% of the contaminant is dissolved in groundwater and 20% is adsorbed to the aquifer solid. C is a total contaminant concentration is 5 times the dissolved concentration with 20% in groundwater and 80% adsorbed to aquifer solid. And D is the contaminant is unaffected by aquifer material and behave like a conservative tracer. So if we have retardation factor 5, what that mean? Okay, so Priscilla and Amrutha gave me C answer. So I will also go with that C answer only. So if we have the retardation factor 5, so this retardation factor 5 is something like 100 plus 100 divided by 20, right? So the 100 is, for example, if we have contaminant 100% in the in aquifer. Okay, so 100% contaminant in the aquifer, but only 20% is in the groundwater, flowing groundwater, because the 80% has been adsorbed in aquifer itself, so it is not moving. Okay, it has been stuck at some places, for example. So this is something the retardation factor. Okay, so 80%, and this will come, so 80% is in the aquifer out of, so total 100% we had in the aquifer, but 80% has been adsorbed or had been clogged in aquifer, but 20% is in the groundwater. So our responsibility is to reduce that 20% with some technology. We do have a lot of technology by which we can remove groundwater contaminations, but this is something will come under the retardation factor. So C answer is the right answer. So just let me show you the ratio of total contaminant in the unit volume of aquifer to the contaminant dissolved in the groundwater. So this will known as the retardation factor. If it is a 1, then it means all contaminants has been dissolved into the groundwater. But if it is a 5, then 20% has been dissolved in the water, but 80% is absorbed to the aquifer solids. Okay, so this is, there is the one another formula also of the retardation factor, how we can calculate this. So this is something retardation factor. Okay, now we are moving to some numericals related to BOD and some concept related to BOD. And I already have talked about you about the BOD, that it is how much oxygen microbes need to break down the organic compound into some simpler inorganic compounds. Okay, because that organic compounds may give you a lot of problems in the water, and that's how it is the wastewater. Then we do have two different type of BODs. The one BOD is standard BOD, BOD 5, and the one is ultimate BOD. So you need to tell me the difference between these two BOD. And before giving you the option, you already have given me the answer. uh Chitali and Priscilla gave me C answer. Okay, anyway, so I will not repeat the option because you already have read. So we have two type of BOD. The one is BOD 5 and another is ultimate BOD. So the thing is, within that first 5 days, how much oxygen is needed to degrade that organic compound into the inorganic. So this will come under the standard BOD. And the ultimate is, like, we are not talking about, there is a no restriction of time, but the ultimate goal is just to break down that organic compound into the inorganic compound in the presence of microbes. So how much oxygen will be taken up by that microbes for this biodegradation, that will come under the ultimate BOD. So ultimate BOD will always greater than, or it may be equal to, the BOD 5. And there is the question is, why we are taking 5 days, why we are not taking like 6 days or 7 days, why we are just sticking with the 5 days BOD? Can anybody tell me about this? Why we are just taking 5 days BOD, or we are talking about the ultimate BOD, but we are not talking about 6 days BOD, 7 days BOD? Why we are sticking to the 5 day BOD? Okay, so let me show you here. So mostly whenever we have 5 days, right? Whenever we have 5 days here, okay, so that we have organic compound, that organic compound may have carbon, may also have nitrogen, right? The breakdown of this carbon will start from 0 day. Okay, Chitali gave me some answer, but I'm explaining it. Okay, so we have carbon, we have nitrogen into the organic compound, and we need to break down into, let's say, CO2 or NO2, right? But the thing is, this carbon compound will start breaking down from the 0 day, but this nitrogen will start after 5 days, mostly after 5 days. So whenever we are talking about the BOD 5, then mostly we are talking about the carbonious BOD. But after day 5, nitrogen degradation will also start. So this is how we are just sticking to the BOD 5. Okay, because most of the time we are trying to estimate the BOD due to the carbon compound only. Okay, so this is how we are taking BOD 5. But here you can see, uh, up to 5 days we have the BOD 5. Then after that, this nitrogenous, so there will be the breakdown of the nitrogen based compound as well. So this is how, and this is something how much how much oxygen we need for the carbon compound. So this will come under the carbonious ultimate BOD, right? But if we are also adding this nitrogen, so this will come under the ultimate BOD. We are not talking here about just the carbonious, but here we have carbon as well as the nitrogen organic compound degradation also. So we have right now three terminology: BOD5, carbonious ultimate BOD, and then the ultimate BOD. So I think now you can differentiate between these three terminologies. Okay, so for example, if we do have a river, right? And if we are putting, so here we have a pipeline, and that pipeline have the wastewater. And if we are putting that wastewater into the river, then we will have and that wastewater had the dissolved oxygen initially, and this river also had the dissolved oxygen. Okay, but after mixing that, we will have the mixed dissolved oxygen concentration. And the question is, when waste is discharged into a river, the mixed dissolved oxygen concentration can be predicted using, and we have four options here: the average of DO in waste and river, irrespective of flow rates, only the DO of the waste, assuming it dominates the system, the flow weighted average of DO from both river and waste stream, and fourth option is the DO concentration at the critical point of maximum deficit. Okay, I'm getting D answer. I don't know how, but yes, I'm getting D answer. You need to see D answer is right or wrong. Pradeep gave me right answer. C. Okay, so I'm sticking with C answer, and I will explain you why D answer is not the right, but C is the right answer. Let me clear this. Okay, so the thing is, you people gave me D answer, the DO concentration at the critical point of maximum deficit. So this is something will come under the oxygen sag curve. So this is something like this. If we are putting here the wastewater in the river, okay, so what will happen? Dissolved oxygen will start decreasing. Okay, will start decrease, and this is distance, or you can say this is time. You can say also time, and this is the concentration of dissolved oxygen. So whenever you are putting wastewater into the river, then DO will reduce. DO will reduce, dissolved oxygen will reduce, because the BOD will increase, biochemical oxygen demand will increase, and this is how dissolved oxygen will decrease. Then time will come when BOD, the demand will, because most of the organic compound will start degrading. Okay, then again DO will start to rise because of the reaeration. We have river, we have transition of river with the atmosphere. From the atmosphere, oxygen will come. Okay, and this is how there will be the, once again, the DO will start to increase, and this one is known as the critical point of maximum deficit. Okay, but here, because we want to estimate the mixed dissolved oxygen, then what will be the answer? Let me show you. I think I have the explanation. Yes, so this is river, this is river. Okay, I'm just repeating the question. So the question is, when waste is discharged into a river, we will have the mixed dissolved oxygen concentration, and how we can predict that mixed dissolved oxygen. And how we can do this? We can do by using that formula, and that is, we have this river, right? We have this river, and river have river flow, that is QR. River also have DO, that is the dissolved oxygen. River also have BOD. River may also have some BOD, a biochemical oxygen demand. But if we are putting waste into that, that waste also have some waste, that flow rate, so that will come under waste flow, QW. That waste will also have dissolved oxygen, that waste will also have BOD of the itself. And after mixing, what will happen? We will have the combined flow, that is the Q mix, then mixed DO and the mixed BOD. And because we know that the sum of this flow rate multiplication by concentration and sum of this product will be equal to the out of this product, right? So because two things are coming, river is coming, then the wastewater is coming, then the summation of this Q and C will give you the mixture. So this one will equal to this one. So what we are getting is that we have to multiply, this is the concentration, okay, this is the concentration of oxygen, and we are multiplying that concentration with the flow rate. Okay, so the question was like that only. So what we are doing, we are doing flow weighted average of DO, because we are multiplying with the flow rate. We are multiplying the flow rate with the concentration of the river and even of the wastewater, and then we are doing the summation. So this is something average, and this is how we are calculating the mixed DO. So that's how C answer is the right one. Okay, so this will be, and we know that the flow rate mix will be the sum of flow rate of the river and the flow rate of the wastewater. Then this equation will be turned into this one, and this is DO mixed. So DO mixed is the average. You can see the average, right? We have the concentration of DO of wastewater and even in the river. But what we are doing, we are multiplying this with the flow rate and dividing by the flow rate. So this is how we can calculate whatever dissolved oxygen we will have after mixing this river water with the wastewater. Okay, so this is the formula, and right now I have question on this formula only. So if we have the river and river flow rate is 30 meter cube per second, dissolved oxygen of that river is 5 mg per liter, and it receive a wastewater discharge, and that wastewater have the flow rate 5 and DO 2 mg per liter. So can you give me the answer of mixed DO? So mixed DO will be 30 multiplied by 8 plus 5 multiplied by 2 and then 30 plus 5. So this is how we can get the dissolved oxygen after in the downstream of the river after getting mixed with the wastewater. So this is how we can calculate the mixed DO concentration. I think that numerical is very easier for you. So the answer is 7.4114. So this is how you can calculate, very easy. The formula is this one. Okay, let me show you the next question. Okay, here till now we talked about dissolved oxygen, but what if we are talking about the BOD, that is the biochemical oxygen demand? So, and even the same case, we have the river, then some wastewater is putting into that river, then we will have the final concentration of BOD. So here we have some BOD of the wastewater. Here we have BOD of the river. And we want the BOD of the mix. So again, the same formula, just we need to replace the dissolved oxygen with the BOD. So can you tell me the answer for this now? And what will be the formula? Priscilla, B with the question mark. Okay, let me show you. Yes, the answer is 7.6. And this is something, here we are not talking about the BOD5, but we are talking about talking the ultimate BOD. So this is the ultimate BOD, mixed ultimate BOD. This is the BOD of river. This is the BOD of wastewater. This is the flow rate of river, flow rate of wastewater, and this is the summation of flow rate. And this is how we will get the BOD after mixing it, right? So this is, so right now we already have covered the formula of Darcy law. We have covered the formula of mixing dissolved oxygen. We have covered the formula of mixing BOD, right? Okay, the next question is, now we are talking about the oxygen deficit. What do you mean by this oxygen deficit? First, you have to understand. So oxygen deficit is what, so we have oxygen dissolved saturated minus DO that we have in actual. So for example, water can only have the oxygen 14 mg per liter, not more than that. Okay, so what will happen? And actual is, let's say, 5 mg per liter. Then we can calculate the deficit by subtracting the dissolved oxygen actual minus from dissolved oxygen saturated. Ma'am, I'm in law in maths. It is my intuition. Okay, I will try to solve this with very simple like questions only. But anyway, you have to learn, because if you are environmental engineering student, then I think I would suggest you uh, to just solve such kind of question with the equation only. And we have very simple equation. If we are putting that into the equation, we can solve. So don't worry about this. I also studied maths up to my 10th class only, because I had a medical stream. But don't worry about this, you will also learn. Okay, okay, so this is something DO saturated minus DO actual. So this will be the DA, that is the dissolved oxygen deficit. And we already have calculated this one, right? How we calculated? We had QR, DO, R, and then plus QW, DOW, and then QR upon WR. So this formula we know, right? So if we have this formula, from that formula, if we can calculate this dissolved oxygen in the actual amount, and if we are subtracting it from saturated dissolved oxygen, then we will get the oxygen deficit. Okay, and here they have assumed that saturated dissolved oxygen is 9 mg per liter. So can you calculate now? So this is how we can calculate. This is your saturated. This we already know, right? And what we are doing, we are just putting values into that formula and we will get the answer. No, nothing, like no complications into that. Okay. This is okay. So we this rate of change of oxygen with the time will also happen. So because if there is the uh, organic compound, in the wastewater, then what will happen? The oxygen will reduce, and then it will increase up to that level. Okay, then it means at each time step, this oxygen is changing with the time. Okay, so this we can give. So the change in the oxygen, dissolved oxygen per time, is equal to, here we have the coefficient and this is the deficit. Because whenever there is a gradient, so for example, in the river we have low oxygen, in the atmosphere we have the higher oxygen, then what will happen? That higher oxygen will be diffused into the river water, and this is how. So whenever we will have the more deficit of the oxygen into the river, then more of the re-aeration will happen in the river from the atmosphere. So this is something. So this is proportional to the deficit, and this kr is the re-aeration coefficient. So the question is, we have this product krd, and what does it represent? So can you tell me right now? The oxygen concentration removed due to bod, the rate of oxygen consumption due to microbial activity, the rate of oxygen transfer from atmosphere to water directly proportional to water deficit, and the total oxygen demand excreted by the organic load in the river. So the answer will be C. The rate of oxygen consumption by the microbial activity is not equal to the change in the oxygen per change in the per time. This is not equal to the rate of oxygen consumption. Okay, so this is something. Here we already have given you the formula kr multiply by d. So this rate of oxygen transfer, so this is the re-aeration something, and this is proportional to the oxygen deficit. Okay, so here this I already have shared with you. Okay, so again we have the re-aeration coefficient kr. In the last question only we solved, but here we have on which factor it is dependent on. So this is dependent on, whenever there will be high velocity of the water, then re-aeration will be higher. So let me show you the formula. So this is something, kr is equal to 3.9. This is the velocity, the under root of velocity, and this is the depth. So whenever we will have more depth, then the re-aeration will be less. This is something like this. I'm just moving fast. This one I want to skip right now because you can okay, the thing is, this re-aeration coefficient will be different at different temperatures. So there is a one formula by which we can calculate re-aeration coefficient for different temperature of your river water. So so if we have, and this is something like this, we have re-aeration coefficient when temperature is 20, then we have to multiply it with the theta, something like theta, and t minus 20, and this is the temperature. And the question is, what is the value of this theta? And the value of this theta is 1.024. We most of the time we use uh, this value for the theta. Okay, the another one is uh, the we already have talked about the regeneration, right? But if we are talking about the depletion of the oxygen, then depletion, the rate of depletion of oxygen will be equal to kd and l theta. So this is the ultimate bod, and this uh, kd is the degeneration coefficient. So the answer will be, and here I asked L theta. So this L theta is the ultimate BOD remaining at the given hydraulic retention time. And we again have some value of this theta, and this theta value will be 1.056. Okay, coming to the, because I need 5 minutes more for this water related, then we will go to the air related, right? Now, because we have talked about the property of the wastewater, then how we can calculate that, how we can calculate BOD, how we can calculate dissolve oxygen, then how we can calculate the rate of change of oxygen with the time. We already have understood this, right? But you must also have to understand that because of the wastewater, a lot of diseases is around in the world. Okay, and you have to tell me which heavy metal, if we have in the wastewater, that will give you the itai disease. So this is because of what? Priscilla, Pradeep gave me D answer. So yes, Chitali also gave me D answer. So this is cadmium. If we do have cadmium in the wastewater or in the water, so that will give you the itai disease, and that will give you the bone pain and fracture. And that happened in the Japan, because there was one industry, that industry released cadmium into the river, in the sewage water, and then in river, and a lot of people in Japan got this bone pain and fracture, and that kind of disease is known as the itai disease. So something like this. So such kind of disease we can have. Okay, the another disease is because of the manganese. If we have manganese in the wastewater or the water that we are drinking, what kind of disease we can have because of that? Pradeep gave me C answer, Parkinson. Yes. So this is Parkinson disease that we can have because of manganese. And here you can see, like, you will have the hand tremor, then you will have the flexed elbow and wrist, the back will be rigid, and you will have the tremor in the legs. So such kind of disease we may have because of the manganese. So that's how it is very important for us to drink uncontaminated or unpolluted water. Okay, so this is the disease that we have due to high concentration of nitrate or nitrite in the drinking water, and this disease is known as what? Pradeep gave me C answer. Venkateshwara, Priscilla also gave me C answer. Yes. Chitali also gave me C answer. So yes, so this is methemoglobinemia. So what is that? We have hemoglobin, right? We have hemoglobin, and whenever the nitrite will react with this hemoglobin, it means we had the combination of hemoglobin with the oxygen initially, but this will not be the case. Okay, this oxygen will be removed from the hemoglobin, and if we do not have oxygen attached to the hemoglobin, that this will give you this bluish color in the babies. And this is mostly in the babies because this nitrate to nitrite, so this is something, the reductive environment is present in the stomach of the baby only. So in adult we do not have such kind of condition, but in babies this nitrate can be easily converted to nitrite in the stomach, and this is how whenever this nitrite will combine with the hemoglobin, so this oxygen will be removed, and this is how this will give you the bluish coloration of the body, and this is something known as the blue baby syndrome. You can read about this. I will share the slide. This let me skip. Okay, now we are going to the air pollution related question. Ma'am, it causes death in babies. Yes, it can. There are some cases because of which the death is like, yes, That is possible because of this case. Okay, now we have air pollution related questions. The very first question is, we have some dust particulate matter in the environment, but what size of that particulate matter is important for us, that will give you the problem in your lungs. So the particle larger than 10 micrometer, smaller than 0.5 micrometer, in the range of 2 to 4 micrometer, and it doesn't have any impact on the lungs or equally impact. Okay, I'm getting B answer and then C answer also. Naran Bhai Patel also gave me C answer, and Priscilla. Okay, so I'm going with the C answer only, because let me give you the right explanation. Okay, sorry. So the right explanation is, if we have more than 10 micrometer size particle, then it will not go to the lungs. That will be trapped by the hairs that we have in the nose only. So these are not harmful for us. Okay. If we have particles smaller than 0.5 micrometer, then this will not be deposited, because there is the Brownian motion, and even there is a random movement of this particle, because this it is very difficult for this to deposit in the lungs. So whenever there is a breathing or like inhaling and exhaling, in the exhaling it will come out, so it will, no doubt, it will go up to the lungs, but it will not be deposited, it will go out, okay, in the exhaling. But if we have particle from 2 to 4 micrometer, that will go to the lungs, and that will be deposited into the lungs. Okay, that will not go under the Brownian movement, if you have heard about this. So the thing is, 10 micrometer will not go to the lungs. 0.5 micrometer, less than that, that will go to the lungs but will come out. But if we do have the range of 2 to 4 micrometer, then it is very difficult for us uh, to make it out from our lungs. So that's how this is very dangerous range. Okay, so we have the global warming, right? And you have to tell me which one is not causing the global warming. We have methane, nitrous oxide, stratospheric ozone, and sulfur hexafluoride. Can you tell me the answer for this? Pradeep gave me answer C, that is the stratospheric ozone. Okay, so no, I think Pradeep, you changed from right answer to wrong answer only. So answer is yes, it will be the stratospheric ozone only. And why this is, global warming is due to greenhouse gas. You people know that. Some greenhouse gas and some another gases. And if you know the terminology, the one is GWP, global warming potential. Okay, and this is comparison to the carbon dioxide. So for example, if we do have 1 kg of carbon dioxide and 1 kg of methane, which one will give you the more warming? So as comparison to the carbon dioxide, methane will give you the 21 times more warming than CO2. So this will give you 21 times more warming than CO2. This will give you near to 275 times more more warming as comparison to CO2, because we are talking here about the global warming potential. This sulfur hexafluoride, this is like, I don't know exactly the number, but this is more than 10,000 times. Okay, so this compound sulfur hexoxide, if this we have in the environment, then the potential of this to warm the to warm global is like the power is 100 time, 10,000 time more than the CO2. I don't know the exact number. You can search about this number, but as comparison to the CO2, this SF6 is like can give you the warming in a huge amount. And if we do have the stratospheric ozone, then stratospheric ozone is not giving you the global warming. But if there would have been the tropospheric ozone, if there would have been the tropospheric ozone, then this would give us the global warming. But if we are talking about the stratospheric, then this is not giving you the global warming. So something is like that. We have the vehicle is giving you the NO2. NO2 can give you rise the ozone production near to the surface, then this will give you the global warming. But if we do have a stratospheric ozone at near to a 20 kilometer or 15 kilometer at the height in the atmosphere, that will not give you the global warming, right? Ozone SF6 is a ozone breaker. I'm not sure about this, Pradeep. I think you need to search it, but I'm not sure about this, either it is ozone breaker or not. I think it should be because it have the fluoride, but I'm not much sure about it. Anyway, so moving to the next, we do have two type of NOx, that is the nitrogen oxides formation in the combustion processes. So for example, if we have diesel or petrol and we are having the combustion, okay, in the vehicle we do have the combustion, and that combustion will produce NOx, that is the nitrogen oxide. So we have two type of NOx, that one is the fuel NOx and another is the thermal NOx. Then you have to differentiate between these two. What do you mean by fuel NOx? What do you mean by thermal NOx? So can you tell me the difference between these two? I think based on that we have the answer as well. Okay, so Pradeep gave me C answer. Um, okay. Anyway, so let me show you. Yes, answer will be C. So let me show you. If we have atmospheric nitrogen, okay, if we do have atmospheric nitrogen and that is combining with the oxygen at the high temperature, that will give you the thermal NOx. But whenever you have within your fuel, you have nitrogen compound and that is reacting with the oxygen, that will give you the fuel NOx. Okay, and this is a little rare because for that we need very high temperature. If in the combustion of the fuel in the vehicle we have very high temperature, then only atmospheric nitrogen can react with the oxygen that we have again in the atmosphere. So we do have two type of NOx formation. The one is from atmospheric N2 and another is from nitrogen compound that we have within the fuel only. So based on that, we can classify whether it is thermal NOx or fuel NOx. Okay, this is very important. We have diesel, petrol, right? And in that diesel or petrol, we used to add something into that so that we can reduce the knocking in the vehicle. And then later on, it has been banned because it had neurotoxic uh, air pollutant emission because of that. So can you tell me what was that? Okay, everyone gave me C answer. Yes. So this is tetraethyl lead. So once upon a time, we used to add lead into gasoline so that because lead had the anti-knocking property. And but later on, we got to know that if lead is present in the atmosphere, that can give you a lot of neurotoxic disorder in the human body. So that's how this has been banned. Let me show you. So this is the structure of tetraethyl lat, and uh, two scientists, that is the Thomas Migley and Charles, they only discovered that additive, and but later on this additive has been banned in USA. Okay, so in the vehicle only, if we are having the combustion and that combustion is releasing carbon monoxide, so what kind of condition, in what kind of condition that happened, that CO2 is released uh, in place of CO2? What may be the possible region? Priscilla, Pradeep gave me C answer. Yes, I will also go with the C answer. Whenever we will have the sufficient oxygen or low temperature, low mixing, then we can say in place of CO2, that combustion will lead to the release of carbon monoxide. Okay, and what kind of impact we may have in the carbon monoxide? So this is something like this. The affinity of hemoglobin to attach with the carbon monoxide is nearly to 200 times more as comparison to the oxygen. So whenever we will have the carbon monoxide in the environment, then in place of oxygen, hemoglobin will attach to the carbon monoxide. It means we will not get the sufficient oxygen in our body, and what will happen, so this will give you the condition carboxyhemoglobin, and because of that suffocation, people may die if the concentration of CO is large. And okay, so this is something like this. If you want to calculate the carboxyhemoglobin, so this is the saturated percentage of carboxyhemoglobin in your body, we can calculate it using this formula. So this is the concentration of CO2, this is beta, we have some value of beta, we have some value of uh, this eta, and time. So this is something exposure, how much time you are having this CO. So based on that, you can calculate the percentage saturated carboxyhemoglobin in your body. So the question is, which of the following statement about this equation is correct? So this is something like this. The equation shows that carboxyhemoglobin saturation increase with increasing CO2 concentration and exposure time. So whenever we will have more exposure time and more CO2 concentration, then uh, carboxyhemoglobin saturation value will increase in our body, and there will be the suffocation like problem for us. And this is the formula. And here what you can do is, if you want to calculate the carboxyhemoglobin and you have the value of CO in ppm, eta is 0.402 per hour, and beta is, the value of beta is also given, that is 0.15% per ppm CO, and if exposure time is given, then you can estimate this one. So this is again one more formula by which you can calculate carboxyhemoglobin as percentage saturation. So I have one question related to this. So this is like this. If the CO concentration is given 1200 ppm, exposure is also given 0.5 R, then can you calculate so what time? So the first thing is, first you need to calculate this carboxyhemoglobin percentage, and then the second question is, uh, if we will have the 80% saturation, then what minimum exposure time we must have? So that will be calculated only just using that formula only. So let me show you how you can calculate. So this is something like this. So initially you have this formula, you are putting everything into the formula, so you will get this one. And then if you are having 80%, then you just need to put 80% here, then and CO2 whatever has been given, and you need to calculate T. So this will give you the how much exposure, how much time exposure we need when we will get the 80% saturation of COHP. So this is how we can calculate. If you have any problem, you can let me know. I have 10 minutes now. Okay, the one is photochemical smoke. Have you heard about this photochemical smoke? This uh, this is the reaction of hydrocarbon, nitrogen oxide, and sunlight in the atmosphere. But what will be the product of it? Hydrocarbon, nitrogen oxide, and in the presence of sunlight, if we have this kind of reaction, then what will be the product? Priscilla gave me B answer: ozone, formaldehyde, and pan. Yes, so this is this is the product of the photochemical smoke. So the B answer is the right one. Let me show you something. So have you seen this in the Delhi area? So this is nothing but the photochemical smog. So if we have volatile organic compound from the industries, and we have NOx, nitrogen dioxide because of the vehicle, if we have this VOCs and NOx, and if we have the sunlight, then what will happen? This will give you the smog like condition. Here you can see such kind of smog that we can have, and this is known as the photochemical smoke, very prominent in Delhi condition. You can see here NOx, VOCs will react, and this will give you to the ozone and pan. Okay, if we do have high concentration of benzene, so what kind of disease it may give to the body? If we have high concentration of benzene in the atmosphere, or let's say in the wastewater, so what kind of risk it will give? Priscilla gave me C answer: leukemia. Yes, so C is the right answer. So this is something, the cancer of the blood cell, white blood cell. So what will happen? We have more red blood cell as comparison to white blood cell, but what will happen because of this benzene? White blood cell will outgrowth, and in a very irregular shape, and this is how this will give you growth of white blood cell that are not working properly. So this is how this will give you the cancer. And so the answer is leukemia, and this is how this will happen. So we have red blood cell, white blood cell, and then this white blood cell will outgrow. Okay, very important concept. We have dry adiabatic lapse rate. So can you tell me the value of dry adiabatic lapse rate? We in very first week learned that whenever we are going up, so with the altitude, the temperature decreases. So this is known as the lapse rate. The decrement in temperature with the elevation is known as the lapse rate. And if the air is dry, then what will be that rate? Mm, Mahesh gave me B answer. But just see the unit. Either it is Fahrenheit or Celsius. Celsius. Yes. Yes, it is A. That is 9.8. It is degree Celsius. It is degree Celsius per 1 kilometer. So at 1 kilometer, 9.8 degrees Celsius will reduce. So for example, at the surface, we have 40 degrees Celsius, but after we are going up to the 1 kilometer higher, then the temperature will be 40 minus 9.8. Then another 1 kilometer, this will be reduced again 9.5. So this is something dry adiabatic lapse rate. We have saturated adiabatic lapse rate as well. This is near to 5.6. Okay, and then another lapse rate is the environmental lapse rate. In real environment, what kind of lapse rate we have, and based on that, we like this has a higher advantages of studying this lapse rate, I will tell you. This you already know, that with the elevation in the troposphere only, with the altitude, the temperature decreases, and this is known as the lapse rate. This is something lapse rate. uh, Temperature will decrease with the elevation, so lapse rate. And as I told you, let's say the dry adiabatic lapse rate is 10 degrees Celsius per kilometer. Then initially we had 30 degrees Celsius. Then above that, after 1 kilometer, we will have 20 degrees Celsius, then 10 degrees Celsius, and this is how the temperature will reduce. Okay, and if you have seen this, we have chimney, and chimney is giving you the plume. Okay, and the plume shape is very different. It can be conical, it can be looping, it can be lofting, it can be fumigating, just getting down to the, or down to the surface. This is because of the difference in the lapse rate of dry adiabatic lapse rate at the lapse rate that we have in the environment. So based on that, this shape will be dependent on. Okay, so for example, just I'm giving you one example. This dash line is ELR, that is the actual in environment, actually what the lapse rate we have. And if the air parcel coming from the chimney have higher higher lapse rate means, let's say we have 10 degree per kilometer and environment lapse rate is 5 degree per kilometer, then what will happen? The the parcel of that smoke that is coming from the chimney will cool fast, because that have the more lapse rate as comparison to the environment. And if we have cool, then this will come down. If we do have warm, that will go up. So this is how the environment stability and instability will dependent on this lapse rate. I don't have much time to make you understand, but like I had very like I had figure to make you understand, but I think this is not right time to make you understand. But anyway, if you have any problem, you can mail me about this stability. But based on this lapse rate stability only, it will be decided whether the plume you have from the chimney that will go up, that will go on the ground, or that will go straight. So everything is dependent on the lapse rate. I think you people must understand this, but let's leave it right now. But the another is, let me show you, coming to the formula only. So for example, if we have velocity, we have air, right? So we have air velocity at 10 meter. So this will be known as u1. Okay, and if we want to calculate the velocity of air at some another height, so how we can calculate this? So we do have a very simple formula. U2 is the velocity at some height, and that height is Z2. U1 is the velocity at height 10 meter, and Z1 is the 10-meter height, and we have exponential power p. Based on that, we can calculate, let's say we have smoke coming out of the chimney, and if we do know the velocity of air at 10 meter, then we can also tell the velocity of, let's say, plume at some particular height. But if we do know this p, okay, and this p is very interesting, because that p is dependent on either you are in rural area or in urban area, and what kind of stability we have. And stability is dependent on, again, the lapse rate, and this surface wind speed. So for example, if we have daytime and we have wind speed less than 2 meter per second, then that will come under a stability. Okay, so let's say it is coming under a stability, then under a stability, the value in rural will be equal to 0.07, and in the urban area it will be 0.15. So something like that. First you have to check the stability. After that stability, you have to check the p value in rural or urban area. Then only you can solve the wind speed at elevation zx. Okay, so this is one formula. The second formula is, if you want to, okay, so we have chimney, right? And chimney is giving you the plume, but after the top of that chimney, the plume will rise very vertical and then only will start to move horizontal. So this height, whenever the smoke is vertical in nature, so this will be known as the effective stake height. Okay, and this effective stake height we can calculate using that formula. You can see here, delta h. So this is the effective stake height. If we do have the stake flue gas velocity, stake diameter, wind speed, pressure, so just see that in the environment we need to know the stability of environment, and this will be dependent on wind speed, pressure, temperature. So just see how difficult it is to estimate, or to get to know how this plume will move in the atmosphere after it is getting released. Priscilla, I will share you this recording. Last I already have shared, and this current I will share you tomorrow, I think. So this is how I think you can solve this numerical question. I couldn't solve this one, but okay. If you want to calculate the concentration of that smoke coming out of chimney, so this is the concentration. So there is again one very little complex formula by which you can calculate the concentration that we will have in the ground level or in the any particular distance. We can calculate. This is based on the Gaussian normal distribution. So this is little trickier, but because time has up, so I'm not able to make you understand. Anyway, so this is what kind of air to fuel ratio that we must have so that we can have the complete combustion in the engine, and this is 14.37. You must know this is something like the molecular formula of the fuel, and the molecular formula of air. So we have N2 and we have CO2, then we will add that will give you the total air molecular formula divided by the fuel molecular formula. And this is how for the complete combustion what ratio we should have of the air to fuel, and this is 14.37. And this is how I surrender myself. And thank you so much. If you have any query or suggestion, you can let me know. Otherwise, it is the dinner time. We can have dinner.